So our goal today is putting together molecules that have shared electrons. Unlike ionic compounds, so we looked at previously that were repeating patterns, so NaCl, 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 that's not true of molecules. They have a distinct beginning, a distinctive end. Okay, a molecule like H2O, that's not a repeating pattern. That's all we have. And because we don't have a repeating pattern, it's all you have, you don't get these crazy high melting points to get things to come apart. These individual pieces come apart quite easily. Okay? You know, water at room temperature isn't even stuck together. They're liquid molecules that can move around each other. So we're going to get into our skills that let us predict these molecular formulas with shared electrons. Okay? So when atoms bond covalently, okay, that word goes of sharing electrons. Okay? We can use the structure of individual atoms to predict its bonding capacity. Okay? Does it want to have 1 bond or 3 bonds or 5 bonds or 8 bonds? That's what I mean by bonding capacity. Okay? So we're going to start in group 4A, which the first element is carbon, and by far the most common element you're going to probably see in molecules. We'll do a whole unit in Chem 30 just on carbon. And in biology, you're going to see lots of carbon-based examples. Okay. So carbon's in group 4, using this hybrid orbital Lewis symbol model. 1, 2, 3, there's 4 valence electrons. So we spread them out using our Lewis symbols. The 4 boxes are coming from 1s and 3 p's, sort of mixed together or averaged out. We call them hybridized. So anything in group 4A, like carbon, is going to have 4 unpaired electrons. And unpaired electrons are not stable. They're highly unstable, and they'll want to pair up with another single. So those 4 singles give carbon a bonding capacity of 4. There's 4 of these unstable electrons. We've got a half-filled orbital that wants to be filled. So that covers carbon and silicon. Those are the 2 you might see in Chem 20. Moving on to group 5A, we have nitrogen, 5 valence electrons, 1, 2, 3, 4, and then the 5th creates a pair. So nitrogen only has 3 singles. So nitrogen only forms 3 bonds. In high school Alberta chemistry, you don't see a lot of nitrogen chemistry, but you'll see tons of it in biology. Anytime you see nitrogen in DNA, an amino acid, a peptide, you're going to see 3 bonds off of that nitrogen, or in most cases. Now that's group 5A, so that would cover nitrogen, phosphorus. They all bond the same way. There's a lot of repeating patterns. This unit is very repetitive because we really only have 4 potential periods that are going to bond, 4A, 5A, 6A, and 7A, and they all bond the same. So there's really only 4 categories of non-metals and how they bond. Move to 6A, we get to oxygen. 1, 2, 3, 4, 5, 6. Okay. 2 of the orbitals are filled. 2 of the orbitals have a single electron. There's 2 single electrons, and that's why oxygen or water is H2O. Water, oxygen, and water forms 2 bonds. Group 7A, we have fluorine. 1, 2, 3, 4, 5, 6, 7. 3 pairs that don't do any bonding. Okay. Refer to those as lone pairs. There is 1 single electron, and all the halogens only form 1 bond. Chlorine, fluorine, bromine, iodine, they all bond the same way. Once you get comfortable with how chlorine bonds, you know, iodine is going to do the exact same thing. Last group, 8A, neon, 1, 2, 3, 4, 5, 6, 7, 8. 8 electrons, no singles. So neon using this Lewis theory doesn't form any bonds. No, everything we're doing is a theory. It's not a law. It's not perfect. It works really well for the representative elements and works really well when you're high up in the table. There's almost no exceptions. As we get lower in the table, we'll run into exceptions, or you will at some point. Maybe not necessarily in this course, but in future courses. One big thing that's ignored is d orbitals. This theory ignores them. Okay, so you can get some bonding with d orbitals. When you're way up high, like in period 2, there is no 2d orbitals. They don't exist, so you don't get any exceptions at the top. Okay, but as you get low and there's 3d, 4d, 5d empty orbitals, you'll see some exceptions. Okay. In grade 12 AP, we'll see some exceptions where noble gases can actually bond. That's empty d orbitals can do that bonding. Okay, so ending on that message, all of our theory is assuming there's only s and p orbitals, there's only 8 dots, and that's why using top, bottom, right, left for those 4 pairs. So we ended up with we have 3 possibilities of what's going on in an orbital. Okay. We could have an empty orbital with no electrons in it. There's not much to talk about there. It's just those orbitals could potentially get filled with electrons, but we're not going to see that in this course at the moment. Okay. You could have a half-filled orbital that has 1 electron, and this predicts the number of bonds. Okay. We call those bonding electrons. I know that's in our notes somewhere already yesterday. We can have filled orbitals with 2 electrons. These are referred to as lone pairs. They seem irrelevant right now, and they are for putting things together, but these lone pairs affect our shape. Lone pairs of electrons will repel each other, and they'll make certain structures bent. So when we get to Vesper theory in a couple lessons, these are important, and it's important you draw them in now as a building block skill for our shapes. So we're going to start using just our singles and putting things together right now on the next slide. So using bonding capacity, that's the theory we're using for our examples. And I'm going to start with the simplest example I probably could, hydrogen gas. And I'm going to draw Lewis structures. Sometimes they're called dot diagrams. So hydrogen gas, okay. Science tend to be asked, how does hydrogen come elementally? And you should be pretty proficient at saying it comes in pairs. You just believed us, you didn't know why, you just accepted it. Okay. Why do they come in pairs? Well, a hydrogen atom is in group 1, so it has 1 electron. Okay. You should now identify that as 1 bonding electron. The other hydrogen atom has 1 bonding electron. It's diatomic. There's 2 of them. Okay. Neither of those are stable with 1 single electron, but they can pair up or bond. They can each share their single and fill up their 1s orbital. Okay. Now I'm going to have to redraw this. To draw Lewis symbols, we move bonding electrons to in between the atoms. when you're first learning, you'll tend to draw the top and then the answer is the bottom. Once you've practiced, you'll visualize the top in your head and then right away put them between the atoms when you draw it. Okay. So this is our Lewis structure. Or dot diagram. Writing all the dots can get tedious. So once you go beyond this course, you'll draw structural formulas. In Chem 30, we wouldn't draw any of the Lewis dot diagrams. In structural formulas, the pair of dots gets replaced with a dash. So I'd go H dot dash H. They're faster. Okay? But we want to start with the dot diagram so you really understand the meaning of that dash. Fluorine gas will be next. This is another one of those diatomics. H2, N2, O2, F2, Cl2, Br2, I2. So we have two fluorines. I'm going to be a little bit strategic and think a little bit. I'll say my thinking out loud. I know fluorine is in group 7A. I know it has 7 electrons. It's got 3 pairs in one single. So I'm going to be strategic. I'm going to put the single towards the other atom. And then I'm going to write in the 3 pairs. The other fluorine atom is identical. 1 single, which I'm going to put towards the other atom, and 3 pairs. So the Lewis structure won't let me slide that F over, but the Lewis structure, I'll try this one. No. Okay. I have the dots in between, so I'll leave it. There's my 1 pair of dots in between the 2 fluorines. So that is the 1 bond, and then I have 3 lone pairs around each of the fluorines. Now the structural formula replaces the bonding electrons that I've circled in blue with a dash. Now you're not supposed to show any of the lone pairs in structural formulas, but in Chem 20, we want you to realize these dots. So we encourage you to draw them, even though you're not supposed to in 20, because you have to realize them to get the right shape. So I put them in a different color, because technically they're not there in structural diagrams. But I'm saying to you, write them in the structural, adorn this unit, so you don't make mistakes, so you'll correctly identify something like water is bent, and then you'll drop them when you move on to Chem 30. So that's 2 examples. I'll start going a little bit quicker and we'll get a little bit more complex. We've got water, H2O. So now we have to start making decisions about what goes in the middle. We want to put the highest bonding capacity in the middle, so that it can connect out to as many pieces. So I'm going to do a little bit of thinking. Hydrogen has 1 single, so a hydrogen only is 1 bond, but an oxygen atom has 2 pairs and 2 singles. Oxygen has 2 bonds. So we're going to need to put oxygen in the middle of our molecule. You can't put something with a bonding capacity of 1 in the middle, because it can't go more than one way. So our group 1s are always at the end, hydrogen, and our group 7As are always at the end, or halogens. 1, 2. So oxygen has 2 lone pairs, 2 singles. So those 2 singles are going to be where the hydrogens are going to connect. Hydrogen has 1 dot. So I'm going to put one of the hydrogens to the left. I'll put the other one down. And I'm strategically locating hydrogen's single electron to make things line up. The dots that bond have to be between the atoms. So oxygen has 2 bonds. There's a bond and there's a bond. And there is 2 lone pairs. They're going to affect the shape of water. They're what's going to cause it to be bent when we get to that. So a simpler structure of water, the structural formula, where the dots between the atoms get replaced with a dash and the lone pair dots disappear. Moving on to methane. We've got carbon with a bonding capacity of 4 and hydrogen is in group 1. So right away you're hopefully thinking, okay, hydrogen goes on the outside. So we've got carbon with 4 dots. And this is why we need 4 H's to match that bonding capacity of carbon. There's one of my H's. There's my second. There's my third. And there's my fourth. So that's the electron dot diagram, the structural formula, which grade 12 and post-secondary will use the dashes. You need to read a question carefully and see, do I ask you for the dot diagram structure or do I ask you for the structural formula, and be able to do the correct one for me. So I've only done 1 dash and at 1 pair of electrons. I've got 2 more examples and we're going to see more than 1 dash. We've got ethene. This is a word in Chem 30 you'll start using, but it's not in 20. In grade 12 you'll learn everything with F in it has 2 carbons. Enes means it has a double bond. So I've kind of given away the structure by decoding the name. So I've got 2 carbons and I got 4 H's. We know that things with a bonding capacity of 1 cannot go in the middle. So my 2 carbons have to go in the middle. If I had 3 carbons, I'd put the 3 carbons in a chain. Never put something with a bonding capacity of 1 in the middle. I know carbon forms 4 bonds. And now I've got to kind of figure out the puzzle. I've got to connect up all of those singles. And then I haven't been talking about it, but atoms want to have 8 electrons around them. They want to become like a noble gas. Okay, you know, the 8 can be shared. Okay, and I'll highlight the 8 when I'm all done. So I have 6 single electrons left, but ethene only has 4 hydrogen. That leaves 2 extra dots that aren't going to get paired up until I realize that I can take a second single from each carbon and pair those up. Once I pair up a second set of dots on carbon, then everything's going to work out nicely. My 4 H's match the 4 dots. So when you're putting things together, if you don't have enough other atoms to use up all the singles, you're thinking of pairing up a second set to make a double bond or potentially do it again and make a triple. So I'm going to redraw this. So there's my 2 carbons, and I don't just have 1 pair in between them, I have 2 pairs of dots. So we have a double bond. in both the dot diagram and the structural formula. To show a double bond, every pair of electrons is a dash, so that would be 2 electrons, but I need 2 more, so I have to put 2 dashes. Carbon has a bonding capacity of 4, so you need to have 4 dashes coming off of it. And that's what I have. Each carbon has 4 lines coming off. Okay. Now every atom needs to have 8 electrons around it, okay, factoring in s and p orbitals getting to 8. So if we look at the carbon on the left, and I circled all the electrons around it, I have 4 dashes, which is 4 times 2, 8 electrons. So the leftmost carbon has 8. If I look at the right-hand carbon and circle all the electrons around it, I also have 4 dashes, or 8 electrons. So both carbons have an octet of electrons, 8 electrons. Hydrogen is in the first period of the periodic table, so hydrogen and helium only want 2. So you only see 1 dash coming from the hydrogen to give it its duet. But all the other representative elements want 8, other than hydrogen. So that's our first double bond. We see something similar in oxygen. From Science 10, you should know oxygen gas is a diatomic. You didn't know why, you just blind faith in your teachers. But sometimes blind faith isn't a bad thing. Now we know why. Okay, a single oxygen atom would be incredibly unstable. It would have 2 single electrons. In university, would call those single electrons radicals. My other oxygen atom also has 2 singles. So you can probably see what's coming. Oxygen doesn't have a single bond. 1 single from each can pair up. The second single from each can pair up. Oxygen has a double bond in it. So not all your diatomics are the same. Some have double, some have triples, some have singles. So that's the dot diagram. The dots are painful to draw. We won't do it beyond this unit. We'll use structural formulas, which are so fast to draw. But dangerous because you have to know that there's dots there, that there's lone pairs that aren't drawn in the structural formulas. So that's the heart of what we're doing. We're going to do a little case study, and then 2 slides from now, I've got some practice problems for you to do, and then I'll recap the answers. So be prepared to start applying this pretty soon. This case study both talks about bond length and is some more drawing practice. Now I'm going to skip the dot diagrams and go right to structural formulas. I'm going to look at a whole bunch of 2 carbon molecules. The first one, each carbon has 3 H's around it. The second example, each carbon has 2 H's around it. In the last example, there's only 1 hydrogen around each carbon. I'll actually start with this with all of them. So I connected the carbons together because I put the highest bonding capacity in the middle. Now I've got to get 4 bonds around each carbon. So I'm going to start here. I've got to put 3 H's around that carbon. I'm jumping right to the dashes. So I'm skipping putting a dot on the H and a dot on the C and then pairing them up. And when I put 3 H's there, I've used up all the bonds that carbon can have. There is no single electrons left. There's no bonding capacity left. With that rightmost carbon, it is done. And the carbon on the left, the carbon on the right, same thing. The 3 H's fill it up, and there is a single bond between carbons. When I move to the middle example, we've lost an H. Okay. There's now only 2 H's. And when I do that, and I look at that leftmost carbon, I see 3 dashes coming off of it. So I'm like, that doesn't work. That's not right. I haven't drawn it, but there's another single electron there. And that single electron is going to form a second bond with its neighboring carbon. And when I put that second bond in, I now have 4 bonds around that leftmost carbon. So that's good. That's going to be stable. That's the octet that carbon wants. When I go to the right-hand side and put in the 2 H's, those 2 use up the 4 bonds that carbon can have. So we had a single bond, we had a double bond, we moved to the end. When I put in, I'll put in both of those H's. And we've got way too few of dashes or bonds around the carbons. Both of those carbons need 2 more bonds. That leads to a double bond, which uses up another single dot from each side, and I have to do it again. Carbon can form up to 3 bonds. It can't form 4, so you can't just have pure carbon with 4 bonds. It's due to 3-dimensional structure. We'll come back to this, but if you think of the orbitals, they don't all point in one direction. P orbitals have 3 orientations. You can't get all the P orbitals and the S orbitals all pointing one way and make 4 bonds. At least one of your P orbitals is going to be pointing the other way and need a bond on the other side. So we have a single, a double, a triple. We want to talk about bond length. Okay. As you go from 1 bond to 2 bonds to 3 bonds, there's going to be more energy added in total. So 1 bond, 2 bonds is going to have the energy of the single plus some extra for a double, okay, and even more energy in the triple. And what wouldn't be intuitive, this is just going to be a bit of a memorize, as you go that way from a single to a double to a triple, the bond length gets shorter. Now we're going to dive in a future lesson into a little bit more of what's going on with that triple bond. There's actually 2 totally different types of bonds there. So you'll get more of a why in the future, but for right now, it's this is what we see from a single to a double to a triple. So hopefully between the case study, that original table of bonding capacity, so you probably want to have this table out while you're practicing, or just remember it based on your table. So the noble gases, 8A, no bonds, and then if you go to the left, group 7, 1 bond, group 6, 2 bonds, group 5, 3 bonds, group 4, 4 bonds. That's the trend that you get with the amount of singles that you'll have. So you're going to apply this to these 6 examples. So we've got propene, C3H6, nitrogen gas, iodine solid, methanol, hexane, and then formaldehyde. So they kind of get more complicated as you go. Now nitrogen and iodine, the state doesn't matter, but you should know nitrogen, whether it comes in 1s or 2s or 3s, and iodine is also something you should know the count it comes in. Okay. So recapping the answers for the first 3, then I'll pause again. Propene, We've got 3 carbons. I'm going to jump right to the structural formula. Every dash would be a pair of dots if you did a dot diagram. Then I've got 6 H's. Okay. Now I'm going to do a bit of a strategy you haven't seen me do yet. I can easily erase stuff, and you'd want to do this in pencil. This will not work in pen. But I'm going to start putting dashes in. Now I may have to move them. My N carbon needs to have 3 more dashes. Now I could move one and make it a pair. I'm not sure yet. The middle carbon needs 2 more dashes, and my N carbon needs 3. I'm counting to 4 with all my carbons. Now if I count all my dashes, I've got 8 of them coming off, but I only have 6 hydrogen. So I can't leave all those dashes the way they've been written. I'm going to have to pair 2 of the carbons up. Now it actually doesn't matter which way you do the pairing. You could do it on the right-hand side or the left, but I just took away 2 dashes. That comes from 2 singles, and I'm going to pair it up. Once I do that, I don't have 8 dashes sticking out or 8 bonds left to fill. Now I only have 6. Okay. The 2 dashes were each a single on carbon that I just paired the singles up instead of sending them out to other atoms. Now everything's going to work. This or any rotation or mirror image of this is also correct. Okay. So if you did the double bond between the 2 right-hand carbons, you're also correct. You just can't have 2 double bonds. That doesn't work. Okay. So that's the structural formula for propene. Nitrogen gas. I'm going to do the structure. I'll do the dots second. Nitrogen is diatomic. Now, what's the bonding capacity of nitrogen? 3. Both nitrogens have a bonding capacity of 3, so you're going to have a triple bond between the nitrogens. Okay. How many lone pairs are in nitrogen? I'm going to draw that nitrogen atom out. It would have a lone pair and 3 singles. All 3 of those singles are going to bond, and there would be a lone pair left. Okay. Now, structural formulas, you shouldn't show that lone pair, but I'm adding them in this learning phase. Okay. So you probably didn't draw it like that. So the structural formula has 3 dashes. If you did the dot diagram, you would have had a pair up singles 3 times, then there'd be a lone pair. And that's the most bonds you're going to see. There's a triple bond between nitrogen. Very stable, very short. So that's the nitrogen that's bouncing around in this room. This room is over 80% nitrogen gas. Iodine, fairly similar. It's another one of our diatomics. Well, we have to think how many bonds. Diatomic hydrogen, we saw with 1 bond. Diatomic oxygen has 2 bonds. Diatomic nitrogen has 3 bonds. When you're in a different group, you're seeing a different bond count. Iodine, that's group 7A. It's got 1 single and 3 pairs. So iodine is only going to have a single bond between the I's, not a triple like nitrogen. The structural formula just shows the bonding electrons, just shows 1 dash. So I'm going to pause, let you finish up the last 3, and then I'll highlight those shortly. So I'll wrap up the answers to the last 3. So starting with methanol, it's so important you get the starting sequence right. So don't start with any of those H's. They have a bonding capacity of 1. So we've got carbon and oxygen that have to be in the heart of the molecule. If you can get the C and O connected, then you're probably going to be successful. Okay? Now that carbon needs 3 more bonds, and that O needs 1 more. Okay? And when I put those dashes in, I have 4 dashes and 3 and 1 4 H's. So then it's kind of just putting everything together. So it can seem easy, but only if you got that C to the O bonding capacity of 4 and 2 in the middle. Now I'm drawing these out. We're going to do bond angles next. So this is where structural formula doesn't show these lone pairs, but they're critical to our future lesson. If you don't realize there's lone pairs, you get the structure incorrect. So if you take an oxygen atom and forget that there's lone pairs, you would think that it would be straight. But we need to realize that there's some lone pairs on that oxygen, and when you factor in the lone pairs, it makes that oxygen bent. Okay? And that is super important, and that's what's coming. So that's my comment of why I want you to write in the lone pairs in the structural diagrams, even though you're not supposed to, so we get correct shapes. Hexane. This is a bit long and repetitive, but you need to be able to handle these. C6H14, you've got to get all those carbons out in a row. You don't put any H's in the middle. When you do that, if you start putting in all the dashes and counting, I end up putting in 14 dashes to get 4 bonds and all the carbons, and there's 14 H's. So there was no need for a double or triple bond here. Now, when you're in chemistry 30, I'll give a bit of a hint to knowing whether there's a double bond. I'll mention it now, but it's not needed for this course. Okay? But it can help you. Okay? Things that end in ane just have a single bond, and the carbon count you can use to predict the hydrogen count. It's double plus 2. So if you have 6 carbons, if you double it, you get 12, plus 2 is 14, and that would tell you there have to be all single bonds. Okay. In Chem 30, we'll do enes that have a double bond, and their hydrogen count is just double. So if there were 5 H's, there'd be, 5 carbons, there'd be 10 H's. Here, that can help you. It's a guide to put in a double. The YNE in Chem 30 tells you there's a triple bond, and we've got to take away another couple H's. So if you had 5 carbons with a triple bond, you'd have 10 minus 2, you'd have only 8 H's. Okay, again, but you will not get tested on any of this in 20. Absolutely in 30, I would expect you to know this. Formaldehyde, CH2O. So we've kind of got to go back to putting that C and that O together first. And then how many more bonds do I have? 1, 2, 3, and 1 there. I put in 4 dashes, but I only have 2 H's. So that's not going to work. I'm going to have to put another bond between my C and my O. And I have no choice. I can't go C to C. You can't bond to the same thing. So if I go back a second and do something wrong, I can't take away another bond there. Oops. And kind of like do that. Okay, you can't bond to itself. Okay, hopefully that looked silly. Looks really silly to me. Okay? You have to do the double between 2 different atoms. So I have to take away one of the C dashes, one of the O dashes, and double that up. Oxygen has a bonding capacity of 2, so it's good. Oxygen has a bonding capacity of 4, so when I put in the 2 H's, it's good. Okay. Now, oxygen has a lone pair. Okay. You don't really see the complete solution until you put in the lone pairs. Okay. Is there 8 electrons around that O? 2, 4, 6, 8. Yes. If we look at our carbon, okay, I'm grabbing all the dashes that's around it. There's no lone pairs in carbon. Okay. There's 4 dashes, 4 times 2, there's 8 electrons around the carbon. So we have an octet around our 2 atoms that want 8. Okay. Now there are some exceptions. This is not an AP thing. All Chem 20s have to be aware of some exceptions. So this is all a theory. It's not perfect. It's based on S&P orbitals mixing. It's assuming there's only ever 8 electrons that can go into an energy level. Totally ignores d orbitals. And all of these theory pieces lead to some incomplete answers. So I'm going to start with atoms we've kind of been ignoring. Okay? We've got boron, that's a metalloid in group 3. Okay? And you can even get beryllium doing some exceptions. It's a metal, but it can share electrons sometimes. Okay? Now if we think of boron as an atom, group 3A, so it only has 3 dots. Boron rarely has enough electrons to get to an octet. Boron will often bond and have one of its orbitals totally empty. I just did an empty box to emphasize that there's an orbital there with no electrons. So when you're doing boron, you often want to have an octet. So we'll see examples like BH3. Boron, which can have 3 bonds, it'll bond with 3 H's, it'll have an incomplete octet. Okay? And you have to be okay with this. You have to be aware that this is okay. Now, once you pick up the patterns of this unit, there's a lot of repetition. I could substitute those hydrogens for something else that has a bonding capacity of 1. So I want you to think for a second, where do I find bonding capacities of 1? We did kind of group 1 with hydrogen, group 17 or 7A. Okay? So there's a whole bunch of other examples. I could have boron trifluoride. It's going to look the same as boron trihydride. I could have boron trichloride. It's going to be the same thing. I just kept putting a different bonding capacity of 1 example. Incomplete octets in all of those examples. Okay. We get the same type of thing when beryllium bonds. Beryllium only has 2 electrons. I'm not going to put the boxes in now, but there's 2 boxes with no electrons, 2 empty orbitals. Okay. So you can have beryllium hydride. I'm not done. How many H's do we expect? 2. Beryllium has a bonding capacity of 2, so there's only 2 H's. Okay. So beryllium has 2 single electrons, no lone pairs, and it's important you realize there's no lone pairs there when we get to the shape. Boron also doesn't have a lone pair because it has an empty orbital. Beryllium has 2 empty orbitals. Okay, so that's one set of exceptions everybody needs to know about who does Chem 20 in Alberta. Okay. Then we're going to get into some examples, more so in the next lesson, where there's more than 4 bonds. We're like, how can there be more than 4 bonds? Well, we need some other orbitals, and this is coming from some empty d orbitals. Can allow us to have more bonds. Okay. So we can't have this yet. Okay. Again, in the next lesson, we'll see something like SF6. and you'll get steps for putting this together. Okay. Your first default will be to try to use bonding capacity. Okay. Sulfur should have, how many bonds should sulfur have? Okay. So group 8 is 0, group 7A is 1, group 6A is 2. You'd expect sulfur to have 2 bonds, and there's way more than 6. Okay. So that means we can't use all this bonding capacity. We're going to have to use a different set of steps to solve this. So we'll go through where this comes from in the next lesson. Okay. In terms of AP, we can talk about this hybridization, or what orbitals were needed to make SF6. Okay. It's beyond kind of Lewis theory. Okay. We're going to have to remember S orbital, S, P, D, F. S orbitals, there's 1. P orbitals, there's 3. D, 5, F, 7. Okay. We need to keep mixing orbitals till we get enough to make SF6. So there's 6 orbitals. I'm going to start with S, but there's only 1 of them. Then I can move to P, and I can only use up to 3 P's because there isn't 4, 5, or 6 P's. There's only 3 P orbitals. So sp3. So 1s, 3 p's, I'm up to 4 orbitals, which would give us 4 bonds. But we need 6 bonds, so I have to keep going to D. How many more D's do I need to get to 6? I need 2 of them. So the hybridization of that sulfur isn't 1s and 3 p's like we've been seeing with carbon to get 4 bonds. It's sp3d2 to get to 6 bonds. And this is a common sort of grade 12 AP exam type question. Okay. But I'll put some of this on your unit test. Just count how many bonds is around that central atom, and at mix orbitals you get to that number. So if we had 8 bonds, we'd need 8 orbitals. sp3d4 would get us to 8. Okay. So we've got under exceptions, under the octet rule with boron and beryllium, and then we could see some examples with more than 4 bonds. You don't see that in period 2 because there's no d orbitals in period 2. But once you get to period 3, 4, 5, 6, there are d orbitals that can exist. Okay? If we think of period 4, okay, there's the 3d orbitals. They might be empty, but they exist. Okay? Period 5, there's the 4Ds that do exist, even if they're empty. Last bit, polar bonds. We're talking about sharing electrons. We don't have ionic bonds where something robbed and something got robbed. If you have sodium chloride, sodium was robbed blind. Sodium lost a whole electron, chloride gained a whole electron. Okay. That type of sharing, which isn't really sharing in ionic, is myself and another teacher are going to share $10. Ionic bonding is I get 10 and he gets 0. Unequal sharing, okay, which is not even really sharing. That's ionic. Okay, we're going to get into, we're doing covalent bonding, sharing. Okay, first bullet is non-polar covalent bonding, equal sharing. I get $5, the other teacher gets $5. That's perfectly equal sharing. Okay, in chemistry speak, you could share electrons, you evenly share them. Non-polar, there's not a buildup of charge at one end. There's no poles. There's no negative side and positive side because it's perfectly balanced. Okay. We're going to see this word polar. Okay. We've got a north pole to the planet. We got a south pole to the planet. But we're not talking about magnetic poles. We're going to talk about electric poles. Okay. And I'm saying there's no poles here. Then we have polar covalent. There is a positive end and there's a negative end. So one side has more electrons, it's negative. The other side has less, it's positive. Unequal sharing. Myself and another chem teacher, we could share $10. I'm keeping 8 and they're keeping 2. That's still sharing, right? I've got 2 kids, that's how they might share. Okay? They're going to share their Halloween candy. One gets 8, one gets 2. Okay, the older gets 8, the younger gets 2. Okay? It's still sharing. Okay? It's not ionic. Okay? And there'll be a negative end and a positive end. There'll be a happy kid and there'll be a sad kid. One crying, one cheering. Okay? So how do we predict this sharing? Okay, with candy, you expect the older kid, the bigger kid gets more candy. Okay? In chemistry, one of the atoms has a greater attraction for electrons. Now, we talked about electron affinity already, but we have a different measure. It's the same concept, okay? But it's called electronegativity, is a value for how strongly an atom attracts electrons. So bond polarity can be predicted by comparing the electronegativity of 2 atoms. So in your Chem 2030 Alberta data booklet, you've got all of these values in there. You don't have to memorize any trends. So if you flip to your data booklet, the highest electronegativity, which we knew from electron affinity, as you go to the right, except for the noble gases, it goes up. So electronegativity increases as we head towards our noble gases, but the smallest atom has the biggest value. It has the least distance between the incoming electrons and its protons. Fluorine has your highest value, 4.0. It's right in your booklet. You don't memorize it. It's right above the atomic symbol. Okay? The lowest electronegativity. What is the weakest person for attracting electrons would be francium. That value is 0.7 compared to 4.0 for fluorine. So as you go up, the attraction for electrons gets higher as you go to the right, not counting noble gases. So that's how we're going to decide this equal or unequal sharing and the greater side. So we're going to look at an electronegativity number line. Now I put electronegativity, but I'm actually going to look at the subtraction of 2 values. We're going to look at 2 atoms and look at the difference. Now the difference, sort of using the absolute value, the bigger minus the smallest we could get would be 0. Zero is our non-polar covalent. I'm going to leave out the word bond. If we have no difference in electronegativity, the bond will be perfectly equally shared. It'll be a non-polar covalent bond. So we need to have a difference that's 0. The easiest way to have a difference of 0 is have the same atom on both sides. Diatomic oxygen or diatomic anything. Oxygen is 3.4 for electronegativity. Both O's are 3.4. Both O's are pulling the same amount on those electrons. So they tie. So they share them equally. Okay. I'll do a couple more examples, but again, any of the diatomics. They don't have to be diatomics, but the bond count is irrelevant. It's the difference between the right and the left, which has to be no difference when it's the same atom. So that's equal sharing. Then as the difference gets slight, you're going to get polar covalent. Maybe you have a carbon and a nitrogen. Nitrogen is 3.0 where carbon is 2.6. So they're not the same now. The nitrogen's a little bigger, the carbon's a little bit smaller. So nitrogen pulls on these two shared electrons a little bit more, so those two electrons are a little closer to the nitrogen. And we kind of have to think of our quantum mechanics and our wave and our orbitals. You remember like an s orbital is a sphere and a p orbital is two lobes? We're shifting those lobes towards the nitrogen. We don't know where the electrons are, but we're more likely to find it close to the nitrogen than we are close to the carbon. Okay. So nitrogen is bigger. This will be our slightly negative end. The carbon will be the slightly positive end. This delta sign means slightly. Okay. The bigger electronegativity is the nitrogen. That has the greater pull. Okay. Nitrogen is the big kid. Carbon is the little kid. So this difference was 0.4. Okay. We find that there's still sharing all the way up to 1.7. This is a rough guide. This isn't a rule, but it's a really good trend. If the difference between the two atoms is less than 1.7, there's still some sharing. Once the difference gets above 1.7, we would predict ionic bonding. And this is where that generalized science 10 rule came from. When do we see big differences? Okay, differences greater than 1.7. Well, we want to take the really big numbers, our nonmetals, and we want to take our really small electronegativities, our metals. And in general, as a loose science 10 guide, which works really well, metals and nonmetals tend to be ionic. But we're overriding that rule now. You have a better understanding now. You would now expect sodium chloride to be ionic because of its difference in electronegativities. And that can fail. You can take something like aluminum and find some nonmetals that don't have a difference above 1.7. You can get aluminum that's a metal to share electrons and be not ionic. So that science 10 thing is gone, vetoed, out the door. Do not call ionic things metals and nonmetals anymore. So if we had sodium fluoride, and we want to know what type of bonds we're going to have, we had looked at the electronegativity of the biggest minus the smallest. Fluorine in our data table is 4.0. Sodium, right above sodium is its value, it's 0.9. You do the subtraction and you get 3.1. That is way bigger than 1.7. The outcome of that difference is you would expect ionic characters of the bond. So we have this uneven sharing. Even sharing, $5, $5. Uneven 6 and 4, 7 and 3, 8 and 2, 9 and 1, 9.5 and 50 cents. At some point, it goes to 10 and 0, and that's ionic. Okay? And we predict this 1.7 is a guide to predict when we get this flip over from a little bit of sharing to no sharing. Okay? So we've gone through a lot so far today. You really need to practice putting things together, focusing largely on molecules. That's our goal here. We're not really doing ionic compounds, even though you could make predictions. And then we're going to go deeper into shapes and bond angles once we finish up all of our skill set here, skill sets of putting things together. So we finished putting together molecules. Next lesson is molecular ions.